Now with the handheld pendulum, measured 60 cycles of a 100 centimeter pendulum and 60 cycles of a 25.6 centimeter pendulum. Got a mean of 2.030 seconds for 60 sequentially timed cycles of a 100 centimeter pendulum and 1.022 seconds for 60 cycles of a 25.6 centimeter pendulum. Now, standard deviation of of the individual times for the cycles was 0.085 seconds for the 100 centimeter pendulum and 0.057 seconds for the 25.6 centimeter pendulum. These weren't independent observations, they were sequential observations. So all this really tells us is that we're pretty sure that the total time we got for the 60 cycles was within a couple of standard deviations of the actual time, within a couple of standard deviations of the single cycle times. So we postulate that, okay, I think that the total time for the 60 cycles was plus or minus 0.2 seconds from the actual total time. I don't think that because the individual timings vary by only this much, that it's likely at all that there is more than a 0.2 second uncertainty in the total time for the 60 cycles and a 0.12 second total time for the 60 cycles of the shorter pendulum. That leads me to conclude that, well, 60 cycles with a total uncertainty of plus or minus 0.2 seconds means there's only about 0.003 second uncertainty per individual cycle, even though the uncertainty for any individual cycle might be much greater. Averaging over the whole 60 cycles gives us only this much uncertainty, and an uncertainty of about 0.002 seconds for the mean of the shorter pendulum. So these are the results, and these are the approximate uncertainties. Now, if we compare these with the results that we got for the anchored pendulum as opposed to the handheld pendulum, we see that a slightly shorter pendulum, a 95.6 centimeter pendulum, as opposed to a 100 centimeter pendulum, had a period of 1.96 seconds with an uncertainty probably of 0.005 plus or minus seconds per cycle. So, question is, based on this, what would we expect the period of a handheld, of an anchored 100 centimeter pendulum to be? Well, we've got our model, and we can plug into our model. We can actually just do a simple approximation. I'll maybe talk about it at the end, but one way or another, we find that this is significantly greater than the time we would expect for a 100 centimeter anchored pendulum. So the 100 centimeter handheld pendulum appears to take longer per cycle than a 100 centimeter anchored pendulum would. However, if we compare the 1.022 second mean for 25.6 centimeter pendulum, I think there's actually 26 centimeters, but if we compare this with what we got for the anchored pendulum, we find that there is no significant difference, even if you account for a slight difference in the length. So we're left with the tentative conclusion that we really don't know if this one really is longer, but if it is, it's not longer or shorter, that might even be possible, by anything we can measure significantly on a approximately 1 minute timing using our handheld timer. So we see a significant, small but significant difference, just 1 or 2%, for a handheld pendulum versus an anchored pendulum of length 100 centimeters, but no verifiable significant difference for a 25 a pendulum whose length is in the neighborhood of 25 centimeters. So that's all very interesting. Now I did add to the document some data, well, similar data for a handheld 50 centimeter pendulum. And I leave that to you to think about and analyze if you're so inclined. So we can see maybe, it could be there's no significant difference here. There is a small but significant difference here, and there's a slightly larger but significant percent difference here. But maybe we don't have that sort of trend. And it's all very interesting, and it all comes down to the subtleties of this model, and I think air resistance might have a lot to do with it as well.